Good morning. In the previous lecture, we talked about what is the effect of having a scattering in the atmosphere. Okay? So there we saw that if there are the scatters and they are added with the radiance which are that is reaches to the sensor. So due to the addition of the scatters, there will be the hedge effect in the image. It's a it's a kind of layer due to which we can't see the image clearly. If we compare these two images, first one and second one, the second image is more clear, where we can say that, okay, in the particular spectral band that is being sensed, energy within which being sensed by the sensor, we have very less scatters uh, that is added up with the outgoing radiance from the ground resolution cell. Okay. Now we discuss the spatial variability in the scene, and when we talk about the sensor, so as I discussed before, let me draw a schematic over here. We have a satellite based sensor. It looks towards ground. Okay, so let's say at one particular epoch, it focuses to a particular ground resolution cell. So what we say that, okay, at that particular epoch, this ground resolution total upgoing radiance, it reaches to the sensor over here, and also there will be the addition from the energy coming. There will be the addition of energy coming from the atmosphere due to the scattering. There will also be a component of scatters. They are very weak. In that case, we can say that the hedge effect caused by the scatters is less. So what happens over here, uh, when this particular sensor sees this ground resolution cell,
तर तू तो से बहुत पैसा यार
okay, when this sensor senses this ground resolution cell, so energy that is reaches to the FOV of the sensor due to the point spread function are like some surrounding areas you consider over here, surrounding area that surrounds this ground resolution cell. Energy coming from that area is also sensed by this sensor. So every sensor has a point spread function. We can't say that it can specifically focus to just a particular area. Due to the point spread uh, property over there, it also senses the area that surrounds ground resolution cell. Then we can say that sensor doesn't record radiance from a specified area, like I'm talking about over here, but it also senses the surrounding areas. In case of Landsat satellite program, there is an observation 52% pixels, I mean the energy that is contributed from rest of the area outside of the ground resolution cell. Hence we can say that this is our specified area that needs to be sensed, but due to point spread property, of the sensor. In case of Landsat, 52% energy. Like this area contribute only 48%, while 52% energy is contributed from the area that surrounds this ground resolution cell. Obviously, no effect except boundary pixels. So due to this point spread property, there will be more problem when we sense the urban areas, and when we go for the land use changes, where the land use changes very fast. When we are going to demarcate very sharp changes, like we we want to identify the building exterior, like boundary of the building. Okay, in that case, there is very sharp change. There will be problem due to this point spread property of sensor, okay, that causes to sense out even outside of the ground resolution cell area. A transfer function is plotted over here. Like when we consider the ideal lens, ideal lens should have this transfer function as a impulse function, but this can't be uh, this impulsive response can't be obtained by the real lens, a real sensor. So we can say that it is a kind of Gaussian distribution, this Gaussian variation. Okay, so it's a kind of uh, if you consider the center of that particular area, and if you move away from there, so maximum area is sensed from that maximum energy is sensed from that area, while rest of the energy is sensed from the surrounding area. You see in this figure, if we have a point over here, if you see this point through the lens, uh, it will be spread over here. Okay. So conclusion behind this discussion is like a sensor has a specific dimension. Same dimension ground resolution cell can't be this can't be generated. Like if the sensor has certain surface area, when the sensor looks towards ground area element, this will be larger than the dimension of the sensor. Okay, and further, even the surrounding, if we based on our design, if we say spatial resolution is, let's say, 4 meter. 4 meter means size of the ground resolution cell. It is 4 meter by 4 meter. When we consider it is square in shape, 4 meter is the size. Okay, and we say that okay, this sensor is energy that is reflected or radiated from this cell is falling within the FOV of the sensor, but it is not in a practical case. Even the surrounding ground resolution cell energy coming from there, that energy also falls in the FOV of this sensor due to the point spread property. In I think third or fourth lecture, I suggested you to go through these definitions. When we do the energy related analysis, then you need to remember this terminology. What do we mean by radiant energy? It is a total energy radiated in all directions. All direction means 360-degree solid angle, as is shown over here. Now we have another term, radiant flux. So it is total energy radiated in all direction in unit time from the whole body. Then we have a radiant exitance. Now here we define per unit area. This is whole body. It means we talk about when our unit is a ground resolution cell, the smallest area element. This is the unit. Then from all the area, from all the points within this area, how much energy is radiated back per unit time? It is radiant flux. Further, when we talk radiant exitance, here we talk about in terms of per unit area. As you see over here, this is area A, and it's very small area. We can say it tends to 0 when we talk about per unit area. And when we talk about per unit, it will not be tends to 0. When we talk about a point, then it will be tends to 0. Means how much area, how much energy is radiated from per unit from a particular point. Then in that case, we can say that okay, A tends to 0. But when we have a certain amount of energy, it's not it's a watt per meter square. It's power. So joule per second and per unit area. So this is the radiant exitance. How much energy is radiated per unit time, per unit area. Similarly, when we talk radiance and irradiance, there is a difference between these two. Radiance means outgoing energy and irradiance means incoming energy on the surface. So I hope you can read these definitions from the PPT. I'm not going to discuss over here. Our focus now our focus is to discuss about the spectral signature of various Earth surface objects. In the previous discussion, I talked about Earth surface is covered by some major objects like water, soil, then we can say vegetation. We have a snow cover. We have sand. Buildings, they are made up with a concrete. We have a road network that is made up with the material bitumen. And also we have many other features, but their contribution is less compared to these major objects, which are present in majority on the Earth's surface. First object we select for understanding the spectral signature is vegetation. I have a query. What do you mean by spectral signature? Who will tell me?
Sir, may I try?
Yeah, please.
सर जैसे जो पैसिव सोर्स है उससे इलेक्ट्रोमैग्नेटिक जो रेडिएशन आ रहा है और जो फिजिकल जो जितने भी ऑब्जेक्ट हमारे अर्थ में चाहे वो वेजिटेशन हो चाहे वाटर हो कुछ भी हो तो सर कितने एनर्जी रिफ्लेक्ट कर रही है तो हम उसको स्पेक्ट्रल सिग्नेचर कर सकते हैं और कितना सेंसर एब्जॉर्ब मतलब इसको रीड कर रहा है.
So is it a kind of ratio between two energy component, or it's just how much energy is reflected back?
रेशियो कह सकते हैं, ऐसा क्लियर नहीं है उतना, तो कह सकते हैं सर।
All of you kindly do one thing. As I suggested, and I expect you are making the note. So kindly revise the notes of previous two lectures. I'm giving you 5 to 7 minutes time. Just go through the notes uh, that you have already made for the previous two lectures and just see that what I have discussed over there regarding the reflectance. A spectral signature is a kind of reflectance versus wavelength curve. I'm giving you 5 to 10 minutes time. Just revise that. Then after that, I will ask any one of you. Earlier we already discussed about the what do we mean by spectral signature. Okay. Kindly make a note on this. Spectral signature is related to the spectral properties of Earth surface objects in terms of what is the capability to reflect the energy that is incident on that surface. We select this is the ground terrain. We consider a point over here. Carefully see the workflow that I'm drawing over here. Sun as an external energy source. Okay. This is the shape of radiant exitance, that is m lambda versus wavelength. In this form, energy emanates from the sun. It enters into the Earth atmosphere and due to the scattering and absorption, there is a factor T, that is atmospheric transmission, and it changes with respect to lambda. What happens? The energy reaches at the Earth's surface. That energy is roughly, we can say it is a multiplication of radiant exitance into T lambda. Okay. So we call this energy that is incident energy, and it is the function of wavelength EI. It is reflected back over here, and part of energy transmitted and remaining is absorbed. So EI can be written by applying law of conservation of energy, that is absorbed
reflected energy,
absorbed component, that is EA over here. Now we have a transmitted component and reflected component. So EA, again, this is the function of wavelength, plus E transmitted, function of wavelength, plus E reflected, function of wavelength. This is the first medium. And this is the second medium. If second medium is solid, like vegetation, soil, concrete, etc. Okay. So in that case, if second medium is solid, then the transmitted component ET, we can say it is equivalent to, it is nearly zero. So from equation first, now it is EI, that is incident energy, is equal to absorbed energy plus reflected energy. Fine. What we do now, we normalize this equation by dividing left hand side and right hand side by factor EI, that is incident energy. This is the second equation. Now, from equation second, divide it. See, I'm writing in very detail so that you can also write it in a note. This is absorbed component divided by this is the reflected. This is 1, and I think what symbol I used in the previous lecture for reflectance. Reflectance means this will be the reflectance.
Alpha.
Alpha, no? Okay. Even in book you can find a different notation. So it's just you need to understand. Okay, it's reflectance, so any notation can be used for that. Alpha, should I write it? It is a function of wavelength. It is a constant independent of wavelength, or it is a let's say if we have a MCQ. Alpha, the reflectance. The first option is independent on lambda. Monotonically increases with respect to lambda. Varies with respect to lambda. Monotonically decreases for alpha, that is a reflectance of the material. Which option is correct? Let's say if we consider the material vegetation, alpha for vegetation. If I write alpha for vegetation, and reflectance is represented by symbol alpha. So for alpha for vegetation, out of these four, which option is correct?
Option 4, sir.
3.
Option 4.
Sir, 3.
Varies with respect to
So 3.
wavelength.
Third one. Varies with respect to lambda.
Third
Varies
option.
with respect to lambda.
Okay. So, mixed answers I received. Option 3 is correct. See, with in the reflected spectral signature, if you analyze, you could not find a particular. If you can't find a definite trend, like monotonically increases or monotonically decreases. We'll discuss about it. So the option 3 is correct. Alpha varies with respect to wavelength. So what I should write over here? Then I should write respect to lambda plus this is the absorptance. So for absorptance, I use the symbol beta. So beta is a function of wavelength. when you plot this, uh, on the independent axis, we have a wavelength. It is in generally, it is in micrometer. On the dependence axis, we have a alpha, and alpha is a function of wavelength. And what is the range of alpha, by the way?
0 to 1.
100%, sir. Or we can say 0 to 1 or 0 to 100%. But it will go up to 80% because there will be absorption, and so there will not be 100% reflection. So it will be up to 80% nearly.
Okay. Subham Kumar, could you please unmute?
Yes, sir. Yes, sir.
Just seen the figure. That is a graph that I'm going to plot alpha versus spectral reflectance. So on the this independent axis, there is a wavelength, and on the dependent axis, that is y-axis, what should be the range I need to keep over here for the alpha?
0 to 1.
Are you sure it will be not more than 1?
Yes, sir.
Okay, fine. So obviously it is between 0 to 1. If let's say there will be the query, justify your statement, why it is between 0 to 1, how you will derive that? Like how you are going to justify that?
The summation of reflectance and absorption is equal to 1. So that means both if reflectance is 0, then absorption is 1, or if
Correct.
yes, sir.
So overall, this EI, this incident energy, is redistributed into two forms: absorbed and reflected. Okay, and when we normalize it, so 1 is equal to alpha plus beta. So this equation suggests that. So if there is a query to justify, you need to write this equation, the first and second. This second equation, and this is the third equation. So justification could be done on the basis of these equations. You can unmute. Sorry, you can mute yourself.
Okay.
Alpha, now we have derived over here. Alpha varies between 0 to 1. So we can say that 0 less than alpha less than 1. And we can also keep it, we can also write it in terms of percentage. So it will be 0% less than alpha less than 100%. Okay. And this is called as spectral signature. This plot is called as spectral signature. So this spectral signature is the inherent property of the objects, where we see that how with respect to change in wavelength, the reflectance from that material changes. Okay, and if we have a different reflectance uh, at a separate wavelength, it means in a different spectral band from the same material, you can expect different distal number. and it is a kind of many information we are collecting from the same object. We are getting different DN numbers. It means at a different spectral band, the behavior of object is different, and the behavior is represented in a spectral signature over here. So the variability in the spectral signature, where alpha changes with respect to wavelength, allow us to do the remote sensing. It is containing the information of that object, and in a separate band, the changes within the material with respect to lambda in terms of its reflectance is captured. And due to this region, we can able to separate easily the various objects using multi-sensor data, using the multi-band images. So coming back to this discussion where we talk about spectral signature of many objects which are present on the Earth's surface in majority. I have chosen vegetation over here first. This is the spectral signature of vegetation.
सर मेरा एक डाउट है सर।
हम्म।
सर जैसे आप सिंगल बैंड बोलते हैं और मल्टीपल बैंड बोलते हैं, तो क्या हम इससे कर सकते हैं कि जो सिंगल बैंड इमेज है उसमें एक ही वेवलेंथ है और मल्टी बैंड है उसमें मल्टीपल वेवलेंथ है, ऐसे कर सकते हैं सर?
ऐसे तो नहीं कर सकते, and I think many times I taught about this. Okay, let me repeat. That's why I suggest you to kindly go once to the lecture after every classes. Okay, and that's why I'm suggesting to write a note on the lecture. So this confusion will not arrive, but it is fine. If there will be any query, you can discuss with me. Absolutely, there is no problem. I will explain it. The meaning of spectral band, as I told before, the energy is available from the sun at a different wavelength. It varies from, let's say, if we select ultraviolet doesn't enter into Earth atmosphere and we do not use for remote sensing. So we start from VIS, that is visible. Then we have a near infrared, mid infrared, far infrared, and I hope I told you many times to remember the name and a wavelength range. I hope you remember that. So near infrared, mid infrared, far infrared, then we have a microwave. This part we discussed in very beginning in first 1 and 2 lectures. Then after that, we discussed about the atmospheric windows. In the atmospheric windows, with the help of atmospheric transmissions versus wavelength plot, we saw that atmosphere allow only certain part of energy to pass through. Okay. I'm drawing it's a rough sketch. arrow, this direction of arrows, this shows that, let's say this is lambda 1 to lambda 2. There is a availability of atmospheric windows. Then lambda 3 to lambda 4, there is availability of atmospheric windows. I think this is around this thermal band in this region. In this region, we have a VIS and near infrared. Here we have a microwave. Okay. So lambda 1 to lambda 2, lambda 3 to lambda 4, and that range I am plotting over here. This is the, again, this is a discrete, just I am segmenting the wavelength axis on the basis of availability of atmospheric window. And I hope atmospheric window में तो doubt नहीं है किसी को. What does this mean? Sumit, could you please unmute?
Yes, sir.
What do you mean by atmospheric window?
Sir, the certain segment of the atmosphere which behaves like a transparent atmosphere.
Yeah, atmosphere behaves like transparent or semi-transparent medium. It means
Yes,
most
sir.
of the energy passes through the atmosphere without a significant loss. So that is called
Yes.
as atmospheric windows. Fine, correct. So this range, this range lambda 1 to lambda 2, lambda 3 to lambda 4, and this, there is the availability of atmospheric windows in the atmosphere. So what I expect you to remember, the name of various band and their wavelength range. This VIS, NIR, MIR, this FIR, microwave, etc. Okay. Then after that, you need to remember atmospheric transmissions versus wavelength plot. To remember atmospheric transmission versus wavelength plot, this plot, then I think then you remember this atmospheric windows. And if you recall the conclusion that we derived based on this discussion, we can only design the sensor within the atmospheric window. So if I consider this visible spectrum, VIS, in VIS, what we do, we divide it into three parts. Again, it is again segmented, and this is one segment. It is 0.4 to 0.5, 0.5 to 0.6, 0.6 to 0.7. This is which band it will be? 0.4 to 0.5?
So blue.
Correct. This is the blue band. Okay. Now after that, we have a green band over here. This is the green band. After that, we have a red band. In blue, we can design one spectral band. It is called as blue band. One sensor can be designed to sense the energy within 0.4 to 0.5 micrometer. So this is the range of, when we define spectral band B1 over. Let's say this is a spectral band B1 and it is blue. It is designed in blue band. So there is a kind of band pass filter in this sensor that only allow energy to pass through 0.4 to 0.5 micrometer. Then we design the second band B2, that is green band. and it is over here. Now the green band is in a separate wavelength range, in a separate location on the axis, and this range is different. For B2, the range is 0.5 to 0.6. For B1, range is 0.5 to 0.4. It means in one particular band, we have only single spectral band, one wavelength. It's a range of wavelength, and we also define it a central frequency. This central wavelength, it could be 0.4 plus 0.5 divided by 2, so it's 0.45. It means a spectral band can also be defined like it is around 0.45 micrometer and having the bandwidth 0.1 micrometer. This is another way to define the band, spectral band, or it can be characterized on the basis of range of wavelength within which the sensor sends the energy. Okay. Then further we have 0.6 to 0.7, another band. It's B3. I hope it is clear. किसका doubt था ये? Who had this doubt?
Yes, sir.
I hope it is clear to you.
Yes, sir.
Is there still any doubt related to this?
नो सर, एक्चुअली जो पहला लैब हो रहा था तो उसमें मैंने जब उसका पीडीएफ पढ़ा तो उसमें टीएमबी बैंड का एक वेवलेंथ लिखा हुआ था। तो सर मेरे कॉन्सेप्ट में था कि उसमें एक ही वेवलेंथ प्ले कर रहा है रोल, तो सर इसलिए मैंने पूछा।
No, see, if एक wavelength, the meaning of single wavelength is it's a central frequency, central wavelength 0.45. I saw say over here.
Yes, sir.
If we denote a spectral band, and if we say it is at 0.45 micrometer, it means there is a certain bandwidth also. It's not at one particular wavelength. It is within a range. So 0.45 and the bandwidth is 0.1 micrometer. Fine.
Yes, sir.
Okay. So coming back to our previous discussion where we talk about the spectral signature of vegetation. So in this plot, you can see that the changes in the reflectance with respect to wavelength is plotted, and the reflectance is given in terms of percentage, and the wavelength is in micrometer. Many conclusions we can draw on the basis of analyzing the change variation in the reflectance with respect to wavelength. Okay. And as I said before, why we see the variable reflectance with respect to wavelength? Reason is that it's due to internal composition, molecular combination of the object. When we talk the vegetation, and if we analyze its biological property, so if you consider the leaf, then we have a leaf pigments, then we have a cell structure, then we have a water content in the leaf. So cell structure, leaf pigment, and water contents, they are the constituents which are combined together to form a vegetation. Specifically, the major component which are the leaves, and they are the dominant factor controlling the leaf reflectance. Okay, and other parameters which we consider over here, in the range where water content is dominant factor, like if you see this range, it is I think 1.3 micrometer. After it crosses after 1.2 micrometer, between 1.2 to 1.4, if wavelength is more than that level, this is lambda naught over here, not, then in this range, the reflectance from the leaves is uh, is governed by the water content within the leaves. When we see the water content, then we know that absorption in the atmosphere is dominant due to the water vapors, H2O molecules. So the way water absorbs the energy within the atmosphere, in the same way, water is dominant factor over here. So in the same way, leaf also absorb the energy at those particular wavelengths. And if you remember, I asked you like, what are the water absorption bands? So at water absorption band, that also play a role in the atmospheric absorption. At those bands, you can see the value over here. What they are, if you see, I think it's 1.45. 1.45, no, is it? Yes.
Yes, sir.
Sudhir, I think you told me.
Yes, sir. Right, sir.
That time,
1.45.
yeah, it's 1.45 micrometer. I think it's 1.9 micrometer.
Yes, sir. 1.9 and 2.67, sir.
Yes, correct. So it's a 2.67. And I told you to remember this water absorption band. We never designed the sensor around 1.45, 1.9, and 2.67 micrometer. Okay, even in the atmospheric transmissions versus wavelength, to analyze that curve, there is a very sharp valley. Okay, and reason is that there is a kind of resonance within the H2O molecule, and that due to the resonating phenomena, it entirely traps the energy at these wavelengths. And there could be the question in examination, okay, at 2.6567 micrometer, we design a band, a spectral band, and it is used to sense the vegetation, and a certain amount of energy will be given, and the number of bits are given. So what could be the value of this number? So these numbers you need to remember. Okay. And still just see that. Okay, when we talk about the reflectance, why we have considered only 2.6? Why not beyond that? Even in all the plot, if you see that,
Sir, because detectable reflectance is very less after this 0.26, because after the 3 micrometer, radiance
correct.
will start.
Now see, we will correlate our previous discussion, where we derived certain fundamental, certain concepts based on the graph and various analysis. So when we were discussing about the radiant excitance versus wavelength curve, that is a radiated energy from the sun and radiated energy from earth. So there we discussed about the 3 micrometer dividing line. Okay. And we concluded that after 3 micrometer, we have a radiated as well as reflected component both. Now, when you analyze the reflectance of the material, just see over here, in case of vegetation, we have a significant reflectance only till 2.6 micrometer. Okay. And most of the reflectance we have in this infrared range. It's a near infrared band. And it is due to the cell structure. Cell structure is the controlling factor over here. to reflect the energy from the vegetation. When we see the visible spectrum, it's not so, the reflectance is not dominant, and we have a reflectance between 5 to 20%. And just see, we have a peak at green over here. Is due to the leaf pigments, okay, and these two are the at a green, at a blue and red. There is a chlorophyll absorption. Okay. Due to the chlorophyll absorption at these two locations, you have a there is a less reflectance compared to the green. So in case of vegetation, when we consider the wavelength less than 0.7 micrometer, the reflectance is due to the leaf pigments, and there are two values due to the chlorophyll absorption, and highest reflectance we get at a green wavelength. Okay, and within the near infrared band, you can expect a uniform kind of reflectance between 0.7 to 1.3 micrometer. Okay, and it lies within 30 to 40%. Okay, so we have a certain conclusions based on this wavelength versus reflectance curve of vegetation. In the visible spectrum, we have two valleys at blue and red, and we have a peak at green due to the absorption and reflectance by the chlorophyll. The absorption is there by the chlorophyll for blue and red, while chlorophyll reflect more than compared to blue and red at the green band. Now, when there is a transition from visible to near infrared band, so there you can see the very sharp change. This part, a very, very sharp change over here, and the change is from 10 to directly 40%. So this is called as red edge. And we have a strong edge at infrared, changes with the internal structure of leaves. See, now the factor which is dominant for the reflectance, that controlling factor changes from leaf pigment to cell structure. Okay, so strong edge at infrared is there due to changes in the internal structure of leaves and permitting detection of different vegetation in IR, while in visible they may look same, green. And there is an abrupt change in reflectance at the red edge. So 0.7 to 1.4 micrometer, as I discussed before. Here, it's a near infrared plateau where we have a 40 to 50% reflectance. I have a general query related to this graph over here. Why we see vegetation green in color? Who will tell me?
Sir, as our eyes only detect visible rays, so and vegetation reflecting maximum green band, so that's why
Correct.
it is visible green.
When we consider the filters in our eyes, okay, so we have a kind of band pass filter, 0.4 to 0.7. our eyes only pass the energy within 0.4 to 0.7, and the reflectance from the vegetation between 0.4 to 0.7 peak is at green. So this is the reason why if peak is green, so green color is assigned to green energy in green band. This is the reason why we see vegetation green in color. Okay. Is there any query?